Hello everyone, and welcome to the third video of Worksheet 7. This problem is way harder than the previous two and has a lot more involved. The previous two problems were kind of warm-ups in some way to BSTs, and now we're going to look at an actual BST coding problem. It's a big leak up, so it's a lot harder than the previous ones. Don't feel bad if you don't know how to do this one. I think it's pretty hard myself, but hopefully we're going to go through it together. And even if you don't feel confident that you can maybe come up with this on your own, hopefully you can at least see some of the logic here that we're going to go through. Okay, so we basically have this function. It's called is a BST, or it's called broken is BST. Basically what we're going to do is we're going to feed it a tree, and this function is supposed to tell us if this is a valid binary search tree or not. And if it's not, it's going to return false. If it is, it's supposed to return true, but it doesn't work. And we want to basically fix it. So we want to figure out, first of all, why this particular function does not work. Then we want to write one that does work, and we're going to walk through the process now. Okay, so basically, how does BST work? BST, of course, is just going to have nodes, and then it's going to have left children, and it's going to have right children. The main property of a BST that we're going to be checking for, and if you look at this function, it's kind of the body of the function, is the thing to the left of a given node less than that node, and is the thing to the right of a given node greater than that node? Because that has to be the case. So, for example, something like this is a valid binary search tree, because notice everything to the left of 5 is less than 2, everything to the right of 5, or sorry, everything to the left of 5 is less than 2, less than 5, everything to the right of 5 is greater than 5. But notice that something like, say, this is not a valid binary search tree, because 2 is less than 3, so it should be to the left, not to the right. The second we do this, we've broken the tree. That's basically what we're going to be searching for. So let's look at this function a little bit and try to figure out some of what it's doing. So basically it takes a tree node t, which is just going to represent our root node at first, but then every successive node, because it's a recursively defined function. And it's going to check, is t null? And if so, return true. That's just because it's a base case, and hopefully that makes some sense. If there are no nodes in the tree, it technically counts as a valid BST. Little bit cheap, but that's basically our base case. Okay, so then the next condition we're going to do is we're going to say if the left is non-null and the left value is greater than the value of the node we're looking at, we're going to return false. What is that situation? That is the situation where we have something like this, right? And let's say that t is the node 5. So we say if t.left exists, it's the first thing we need to do, null check. If we didn't have this line, we're subject to null pointer exceptions. So that's why we have this line. If t.left exists, if it's non-null, and t.left.val, which is 6, is greater than t.val, which is 5, then we return false. And that makes sense, right? Because that's this situation where we have something to the immediate left of a node that is greater than that node. So instantly that disqualifies us from being a BST, even if every other node in the BST is, correct. Okay, then we have basically the kind of converse condition here, where it says, else if the right is not null and the right is less than the value, then it's also not a BST. That is the situation in which we have something like this, where 5 is t, basically where we go to the right of the tree, and we see that the thing to the right is smaller than the thing to the left. And then we return false, and then we basically have our else condition. If we don't hit either of those, we don't have either of the two situations I just drew up here, we're going to recurse on both the left and the right at the same time and return the and of them. So remember, the and is going to be true when every part of it is true, and it's going to be false when every part of it is false. So in other words, let's say that you have a node t and you have, children nodes b and c. If A is a binary search tree and B is a binary search tree, and both A and B do not trip either of these conditions, meaning that A is less than t and B is greater than t, then the whole thing is a binary search tree, right? That's the recursive structure here. So that's why we have two recursive calls and we're anding them together, basically. Okay. So that's basically what's happening. We're checking for either of these conditions locally in every node, and then we're saying if all of the nodes obey these conditions, meaning they don't have either of these two situations in them, then the whole thing is a binary search tree. Okay, so let's try to figure out, we know that this is wrong from the context of the problem, but let's try to figure out why it's wrong. Let's draw a slightly bigger tree, something like, let's start with 5 again, and we have maybe 3 and 4 and 2 and 6. So basically, the first thing I want to do is I want to prove this is wrong to myself, right? So I want to find a case in which we can feed it an invalid BST and it will tell us that it is a valid BST, right? Okay, so we know that we're checking for these conditions, and if either of these conditions are present within our tree, then the tree is going to be rejected, basically. So we want to create a tree that is wrong, even though it doesn't have either of these conditions, but that the algorithm is going to say is right. Okay, so we're going to start here with a good binary search tree. This is a valid BST, and we're going to try to see if we can manipulate it a little bit to make it wrong in a way that the function will say is right. So the first thing I noticed, the most obvious thing to do would be to do something like this, where you say maybe 2 is equal to, 6. That's a duplicate, so let's not add it, but let's say something like this is equal to 7. Okay, well, this is obviously not a BST anymore, but keep in mind, this algorithm is checking for anything that looks like this and anything that looks like this, and it's going to find it, right? This algorithm is going to see, hey, you have something to the left of a parent that is greater than that parent. This is not a BST. So we've created an invalid BST, but it's going to be caught by our algorithm, so it's not going to work. Similarly, we could do, something like this. I keep putting duplicates in. I shouldn't be. Let's just say it's 1. Same thing's going to happen though. We're going to run through this tree. It's going to say, okay, is the left child of 5 less than 3? Is the left child of 5 less than 5? Is the right child of 5 greater than 5? This is all going to be good. Then eventually we're going to get to a point where we're going to say, hey, is the right child of 6 bigger than 6? It's not going to be, and it's going to return false. So notice here, kind of stepping out a bit, that if we ever try to change the direct parent or the direct descendant of a node, it's not going to work. It's not going to give us the false tree that returns a positive that we're trying to look for right now. Another thing to notice here, though, is that this only checks the immediate child of a tree, of a given node, right? This checks if the left of 5 is less than 5. It doesn't check anything beyond that. It just checks locally. But our binary search tree properties have to hold universally, not just locally, right? Notice, for example, that 4 here, not only is 4 greater than 3, it is also less than 5 because it's to the left of 5 ultimately. So basically, what if we did something like this? This is not a valid binary search tree, right? Notice that 4 is to the left of 6, which makes sense because 4 is less than 6. However, 4 is ultimately reached by going to the right of 5, and that doesn't make any sense, right? Because everything to the right of 5 is greater than 5, whether it's the direct descendant, whether it's a grandchild, whether it's way farther down the tree. You can't have that. So now let's look at this tree a little bit and ask ourselves, are either of these situations present within this tree? And the answer is no, because if you look, all this is checking is that my left child is less than me and my right child is greater than me. Here, left child is less than, left child here, greater than, left child here is less than, left child here is less than. In other words, all the 4 things I circled are all the checks that this algorithm is going to do. So now we've done it, basically. We've created a tree that is not a valid binary search tree, and it's not because 4 cannot be to the right of 5, but this algorithm isn't going to figure that out because this algorithm only checks locally for inequalities, basically. Okay, so now we figured out the problem, right? And we're going to want to write a version that does work. So here's an example of a tree that doesn't work. Okay, so if we want to write a version that does work, we need to ask ourselves a little bit, in a little bit more detail, well, explicitly, why did it not work? Well, the reason it didn't work is because it was only checking locally. It was checking for these 2 cases up here, but it wasn't checking for parents, it wasn't checking for grandparents. And what you might realize if you look at this tree a little bit analytically is that, take this 3 node, for example, in this tree. Okay, so what numbers can be to the right of this 3 node? It can be 4, it could be 4.5, it could be 4.8, whatever, but it can't be 5, right? Well, because we can't have duplicates. And it can't be 6 or something, or 7 or 8, because we know that we are bounded by the parent, basically, right? In other words, it's not true to say that something, it's not strictly true or as detailed as you could be to just say, okay, everything to the right of 3 has to be bigger than 3. No, it's now bounded. Everything to the right of 3 has to be both bigger than 3 and less than 5, right? So if we put an x in and we want it to go here, we know that x must be greater than 3 and x must be less than 5 because we're bounded by the parent. So that's how we want to approach this. We don't want to approach in terms of saying, hey, is my left child smaller than me? My right child bigger than me? Looks good. We want to say, hey, this child has particular bounds. 3's bounds are determined by itself, by 3, and it's going to be determined by the parent of it, which is 5. And we want to take those bounds into account. So keeping that in mind, let's start looking at this skeleton code a little bit. I will restore this to the bad tree we had earlier. So this skeleton code basically has two methods. It's going to have a helper method. It's going to have the main method that calls the helper method. Hopefully at this point, you're used to, with encapsulated linked lists, you're used to this idea that we're going to have a main method that just calls a helper method and passes in some extra arguments. This is a really common design paradigm. It's the first thing you should probably jump to. And there's a big hint here that you should use integer.min value and integer.max value. So what are these going to be for? Hopefully from what we were just discussing, it starts to make a little bit of sense why these might be useful. Because remember, our problem is now that we don't just want to say less than or greater than when we're going to each successive node, we want to bound each node with a min and a max. And so if you're thinking of it recursively, if you look at this first node 5, to the left, the min is negative infinity, basically. It can be as small as it wants. And the right is as big as it wants, right? If we're just adding a node to the left or right of 5. There's no bounds at the start. The bounds only come in as we start going down layers. So we're going to start with basically no bounds. Okay, so we're past the tree node t, so we're just going to probably pass that into our helper method. And then it says to use these two things. So I'm just going to pass integer.min value. And I'm going to pass integer.max value. They don't give you a lot of room on this one. But anyways, we're going to pass these three arguments in. So now I have three arguments. The first one is of type tree node t. And then we have an int, which we know is going to represent the min. And we have another int, which is going to represent the max bound, basically, of our given function. Okay, so now we have the kind of method signature and everything figured out. We have all the tools. So now we just need to write a recursive function. And we can model the recursive function we're going to write down here off of this one. This one is not strictly correct, but the idea is still there, right? Every recursive function has three parts. You have a kind of base case. You have some conditions you're actually checking or some operation you're doing. This is the part where we visit a node. If you remember earlier in the first question, I was talking about what does it mean to visit a node. This would be the visiting procedure, basically. And then we have recursive calls to the other node. So we can base it off these three parts. So the first part is going to be exactly the same. We're just going to say if t equals null, we are going to return true, right? Because that hasn't changed, right? Nothing about that's not the part of the first algorithm that was wrong. If t equals null, we're still going to return true. Another thing you might notice, well, actually, we'll get there in a second. So we're still going to iterate through, and now we're going to change our if conditions. So before we were checking for either of these two conditions up here. Now we want to check the bounds on a function. So how are we going to check that? So we have the min, we have the max. We know that the min is going to represent, of course, the minimum value, and the max is going to represent the maximum value. And we want to do some comparison based off that. So we're basically going to say else if. What are the things that would make our function false? Well, our function would be false if t.val is less than min, or t.val is greater than max, right? So if the node we are currently on is greater than or less than, that's wrong. So we would return false. Okay, so lots of things here to notice. This is going to be the entirety of the body. The only thing left we're going to need to do is the recursive step, but let's talk a little bit more about this step first. First of all, notice there are two conditions here, right? There are two ifs, because we're checking if the left is invalid and if the right is invalid. Here we've consolidated that down to one check because we're just checking if the single node is invalid. Also notice the thing we are checking is different. So look at these situations, right? This is saying, okay, is my left child smaller than me, or is my right child bigger than me? That's what we're saying up here. Now we're kind of checking, rather than checking from the parent, checking the child, we're checking if the child corresponds to the parent, basically, right? We're saying, am I, basically, less than min, or am I greater than max, right? Am I less than the bound that is set for me, or greater than the bound that is set for me, right? So if we're checking 3, rather than checking if 3 has a 2 and if it's less than, and that if it has a right that it's greater than, we're going to check instead if its parent is less than. That's also why we don't need any null checks here, right? Notice there are null checks here because you're going to be checking children, which may or may not exist. Here, we're not doing anything in reference to the children. We're only checking our own value. And of course, if t is null, right? We would have returned true already, so we don't have to worry about t being null. We've already done that null check basically. Okay, so that's that part. And now the next part is we've been using these min and max variables as if they've been set, but they haven't been set yet, right? We've just been assuming, okay, min's going to be the right thing and max is going to be the right thing. So we need to actually set that, and we're going to do it in our recursive step. Okay, so basically we have this so far, where we need to return a call to isBST_helper. We know we need isBST_helper, and we're going to return it first on the left argument, right? And then we need to pass in the min and the max. So keep in mind that the min of 3, when we were checking it, the node we're coming from is negative infinity, and the max was 5. So when we pass in the new minimum of the max, what is the min that 2 can be? Well, it's still negative infinity. In other words, min is unchanged. It's still whatever 3's min was. And that makes sense, right? Because 3 is unbounded in this direction. So if we keep going in this direction, you remain unbounded. Now we need to pass in the max. So what is the maximum number that could possibly be to the right of 2? Well, it's the number we just checked, right? It's t.val. It's 3. Okay. So now we can do the same logic on the right side. So we do an and, just like we did before. And we can ask ourselves basically the same question. Let's say that we were looking now at 5, and we want to, check the 6 node, basically. And we want to place some bounds on the 6 node. So we return, again, a call to isBST_helper. We're going to do it now on t.right. And now we need to ask ourselves, what are the min and the max? So the min of 5 up here, if we're going to the right, is going to be unbounded, because 5 does not have a parent, and to the right isn't going to be unbounded as well, right? In other words, before you place anything, anything negative can be to the right of 5, and anything positive can be to the left of 5, basically, or anything bigger than. These are the bounds, the maximum and the minimum. So we need to pass the right. So we need to say, okay, what is the new minimum bound on 6? In other words, the children of 6 cannot go below what number? And it's just 5, right? It's t.val. Notice that that means that this tree is going to get called out for being wrong. And we say, okay, well, what is the upper bound on all of the right children of 6? Well, because the bound on 5 was infinite, on 6, it's also going to be infinite. So we're going to do basically max. It's just going to keep the same bound that we had before. And then this is basically this whole function. So explaining again what these cases do, basically, is every time we call, we are changing our bounds, right? Basically, if we're going to the left, we know that the minimum bound given to us from the parent is going to remain unchanged, but the maximum bound is going to be now bounded by whatever we were. In other words, whenever we go to the left of 3, we know that we can no longer have a number bigger than 3 at any point in that subtree. And conversely, when we go to the right of something like 5, we know that we can never have a number smaller in any of the subtrees like 5. So you can see that this case now is going to basically say that this tree is wrong, because now we bounded, right, the 6 node to say, okay, 6 cannot have any children less than 5, and it cannot have any children, and it cannot have any children, I guess, greater than infinity. But you'll see that that invalidates it in this case. So if you run this code on this tree, it will no longer work. This is basically how you do it. Don't worry if you couldn't come up with the solution. I think it's a little bit out there. I myself don't know that I would have been able to do it without a lot of prompting in how exactly to do it. But this is basically how it works, and I hope this has been helpful. Goodbye.